Reductionism is really good for fairly uncomplicated systems, breaking down into component parts. The whole world of the stuff we find interesting, it can't work because there's not enough component parts, there's not a blueprint that has enough elements in it, and because of the role of chance. And what this transitions us into are non-linear systems, non-additive systems, where you break something down to its component parts and you study all those pieces and you put it back together again, and it's going to be different. They've added up differently. You understand the starting point in a system, and you are going to have no predictability about what the complex form is about because the pieces don't add up in a straight linear manner. Okay, what do I mean by this? As we begin to approach this, what is chaoticism about? Here we have a distinctive thing. We have a difference between two different ways in which things can be deterministic. Here's a you're just coming up with a number series, and there's a rule. There's a rule which determines what the next number is going to be in the sequence, which is just add 1. This is a determinist system. It is a periodic one in that knowing what the rule is and knowing which point you're at, someone could say, what's it going to be in 15 steps down the line there? And you don't need to say, well, number 1 is going to be 5, number 2 is going to be 6. You don't need to do that. You recognize a periodicity that allows you to predict pieces way down the line simply by applying the same determinist rule over and over. This would be a system that's both determinist and periodic. Now, in contrast, you can get a system which is determinist but aperiodic, which is where we're heading very quickly. You have some system where there's a sequence of numbers, there's a sequence of places on a three-dimensional matrix, there's a sequence, and there are rules for how you go from each step to the next one. But the thing is, you can't just apply the same rule over and over. You cannot sit here and say, if we start at number 5, and given what the rule is, I know what it's going to look like 10 of these down. The only way to know is to see what 5 produces as the first step, what that produces as the second step. You cannot see periodicity. You could not see patterns that repeat. The only way to know the complex form is to go stepwise and apply the rule over and over again. Because the relationship between any one step here is going to be different from any other one. Here it's always the same. Each one is 1 higher. Straightforward, additive, you just keep doing it over and over again. In an aperiodic system, you have rules, it's determinist, but the rules are such that the spaces, the difference with each step is not constant. The only way you could know what the number is going to be like X number of rounds down is you got to do this, and then this, and then this, and then this. This is an aperiodic system. At any given one of these points, the rules exist for you to know what the next one is going to be. But the rules don't exist for you to know what the 1, 2 down is going to be unless you figure out what this one is. You've got to march through in that sort of way. It's aperiodic. There are no patterns that can be used over and over again. Third version is one that's like that people mistake for what I'm talking about here, which is a system which is non-determinist because there's randomness in there. And in that one, going from this one to the next one, there's no rule. It's totally random what the next number is going to be. And the one after that is totally random. And that one, you have no predictability. You're going to have to go every single step down the line, but it's not a determinist system. There's no set of rules that are being applied over and over again. The nature of this one does not specify the nature of that. It's not determinist in that way. That's not what we're going to be interested in here, where randomness comes in. What all of these nonlinear systems are about, these chaotic systems, are ones where they are determinist. There's rules for how you go every step along the way, but the relationship given any given step is nonlinear. They're not identical, and thus the only way to know what's happening 2 down from here is to know what's happening 1 down. The only way to do that, and thus by definition, this cannot be a system where knowing the starting state allows you to know the mature system without having to go through every single calculation, and knowing the mature state doesn't tell you what the starting state was unless you're willing to do all the back calculations, because it's not reductive in that sense. Where would this begin to sort of manifest itself? Okay, into the Chaos book, and I think it was page 27 or so, that you get the water wheel coming up for the first time, and go and look at this picture, obsess over it, understand what that page is about, because it begins to show how these properties of nonlinear aperiodicity wind up producing chaotic systems. Okay, so you've got this water wheel, and it's got these buckets here, and they've got holes in the bottom, and you can have a very simple steady state. You just put in a little bit of water such that the water is basically, as soon as it gets here, it's running out, it's coming out to the same state. This never fills, the water wheel doesn't turn. Now you begin to fill up at a higher rate, and what that does is it's a little bit asymmetrical. This is heavy enough that it now begins to push the wheel down, and as it's going down, this next one is getting filled, and this next one, and all the while it's emptying out. So constant input of water, a rate of things emptying, the wheel turns. It's possible to get a rate at which you're pouring water into the system where it will do precisely that for the rest of time. It will turn at a set speed. It is a steady state, is in the equilibrium state. It is stable such that if you sit here right now and somebody tells you, in this circumstance like this, the wheel is turning this fast in this direction with this force, you can sit there and you can tell them thus exactly what it will be doing 4,070 years from now on Tuesday afternoon. It is a periodic system. You don't have to sit there and go through every second between now and 4,000 years from now. It is steady state, and you can apply a periodic, there's periodicity, there's a reductive quality to it. Now what you do is you put in the water with a little more force. And what begins to happen is the wheel turns faster, because though it's filling up with water faster, so it's moving this way faster, and that's great, that's totally logical. But at some point, if you're doing that, there's going to be too little time for these buckets to empty out. They're going to start having more water when they're coming up on this side, because it's moving fast enough that they're not emptying, and at some point, there's going to be enough water left here that it will suddenly change direction. Okay. It's possible, if you get the water pressure just right, that you can get a steady state pattern there. It will go around 3 times when you're putting water with this speed. It will go around 3 times at this speed and with this force, and when it has gone around 3.73 times, it will change direction for 1.7 turns, and then it will go 3.7 times around. And once again, it's a periodicity. It's simply a periodicity with 2 components to it. 2 changes of directions. First time, you're going this way, and oops, this fills up. So you have your first change of direction, and then at some point the balance is such that you get your second change of direction, and you start the process all over again. There's a pattern, a periodic pattern to it that just happens to have 2 components. You've doubled the number of components in it by putting more force in the system, but once you understand that rule, okay, at this speed, at this rate, with this force of water, it's going to change direction at this point for this length of time, then it's going to change direction again. Knowing that, you can now sit here and be told exactly how full, how fast, with what force, and you could now tell exactly what this water wheel is going to be doing 4,700 years from now. It is still a reductive periodic system. Now you put in the water with even more force. And what you begin to see is, as the wheel is moving fast enough, it will have sort of this first spin in this direction, and then it will change direction. And because the buckets are now emptying out that much slower compared to the rate at which the water is coming in, it will change direction once more, and once more back this way. And you're back to your starting point. In other words, now we have a completely periodic reductive system that has 4 components in it, 4 changes of directions before you get back to exactly the starting point and do it all over again. You've simply gotten a more complex version of a totally predictable periodic system. And what you see is, as you put in more and more water force in there, you keep getting doublings of your periods. You will now get spinning where it goes through 8 changes of directions before it starts the exact thing over again. And doing that, and you can still predict 4,000 years from now, 16, 32, all of that. And throughout, you can be graphing in a sort of a way of representing it. This is the simple system here. That's the single rotation. Here's when you get a first doubling, and it does something like that. Here's when you get the point. You can represent it that way, and you see it is still, you let it keep running like this, and there will be the same periodicity, the same pattern that will go over and over for the rest of time. It's still a reductive periodic system, it's just gotten more complicated. And then, somewhere in the doubling process, something happens. And the something that happens is, it becomes a non-linear, chaotic system. As you increase the force on the system, the force here being the force of water coming in there, at some point with the force of water increasing, it's going to stop this perfect periodic doubling of the components, and it's going to shift over to a chaotic pattern now. How do you define that as a chaotic pattern? It will shift over to a pattern of spinning this way and then back for a while and going this way. It will generate a pattern which never repeats. There's no periodicity anymore. It generates a pattern that is going to be infinitely different along the way because you're putting that much force in the system. It has become chaotic. And what is obvious here as an implication is knowing here gives you no predictive values ability of what's happening 4,000 years from now. The only way to know what's happening 4,000 years from now is to study what the wheel does for 4,000 years. You can't sit there and recognize a periodicity and just do it over again and again. And what the discovery of chaos was about was that in structured, reductive, linear systems, when you increase the amount of force on it, there's that doubling and quadrupling and all of that. It just gets more complicated and reductive, that there is a transition point where it suddenly becomes chaotic and the pattern never ever repeats and there's no predictability. And sort of the founding generation of chaoticists, this is what they were showing with things like water wheels, where you can see the exact same thing. You have a cylinder, and what you're applying in here, and it's filled with water, and you're applying heat to the system. And what you begin to get after a while is convections, or whatever it's called. Stuff moves, and as you put in the heat it even more, it changes direction. It's the same thing, and at some point when the heat gets high enough, it breaks into boiling, it breaks into turbulence, it breaks into a chaotic system where there's no periodicity, there's no repeating of these patterns. And an amazing insight by one of the first people in the field, this guy York, was that any time you see periodicity of an odd number, you've just guaranteed that you've entered chaotic terrain. That, as he called it, period 3, as soon as you're going instead of a single period, a double, 4, 8, whatever, as soon as you see the first evidence, as soon as any system like this begins to have 3 components before the pattern repeats, it's about to disappear into chaoticism. So this is what a chaotic system is about, which is you have a starting state, and as you increase the force on the system, the periodicity, the predictability breaks down, and eventually you get, as the critical thing, a pattern which never repeats. And thus, the only way to know what that pattern will be doing X amount of time down the line is to run the system from now until time X. There's no predictability from here as to what's happening at X. You got to sit there and march through it because it's an aperiodic system rather than one like this.